Hi everyone! Today we will talk about the third part of Chapter 1, which is the preliminaries in convex analysis. In this part, we will mainly talk about the cone and also several different kinds of cones, including normal cone, polar cone, and the dual cone. Now, let's first recall the definition of convex set. So, what is convex set? As we introduced in previous lecture, the convex set actually means that the line segment of any 2 points inside of this set, then this set will be called convex set. Now, let's introduce the definition of cone. What is a cone? So everyone, I think you eat ice cream, right? So ice cream is actually a kind of cone. Now, mathematically, what is a cone? A cone should satisfy the following condition. For any point x in C and any non-negative scalar lambda, this lambda x must be inside C. Then C will be called a cone. Now, I give 2 examples here. So the first example is that the cone consists by this ray and also this ray. So the 2 rays actually forms a cone. The second example is similar to this one. However, it contains the inner part of the 2 rays, right? So both of the 2 cases, they are cones. Now, there is a definition called convex cone. What is convex cone? It is actually the intersection of cone and convex set. So if a cone is a convex set, then we call it a convex cone. Now, for example here, as we can see that this example consists by the ray x1 and the ray x2 as well as the inner part, it will be a convex cone because it is a cone firstly, and then this set is a convex set. So it is a convex cone. Notice that we got our origin here. Now, we also have some special cases of convex cones. Let's first define open half spaces and closed half spaces. First, the closed half spaces are defined as this x, such that the inner product of x and b are not greater than this beta. These sets will be half spaces. Another corresponding half spaces is defined as greater than or equal to. So both of the 2 sets, they are called half closed spaces. And for open half spaces, it is actually different in the inequality here. Okay, so compared to closed half spaces, actually the equalities are chosen as strictly satisfied. In this case, the 2 sets are called open half spaces. Now, the special case for convex cones include all the subspaces. Okay, so all the subspaces in n-dimensional space, they are actually convex cones. Also, if the closed half spaces or the open half spaces, they are through the origin, then they are also convex cones. Okay, so for general closed half spaces, they are not necessarily convex cones. However, if the closed half spaces, they are through the origin, then they are convex cones. Now, let's introduce the normal cone. Normal cone actually consists of normal vectors. So we first introduce what is normal vector. So a vector is called a normal vector to a convex set C at point A if the following condition holds. Okay, so you can see that this condition is actually an inner product of two vectors. The inner product of the two vectors is smaller than or equal to 0. It is equivalent to that the angle formed by the two vectors are actually greater than or equal to half pi. So in other words, this normal cone, the normal vector, must form an angle greater than half pi with any of the vector here. Now let's take a look at this example. So you got a set AB, all right? This is a line segment, and we consider the point A here. So what is the normal vector of this point A with respect to the set C? So let's draw out the x minus A, this vector. I draw A, B, this set here, and point A here. So for any x, for example, x is here, x minus A is the vector like this. And also it is possible that x lies on this side. So the two vectors are actually represent this part, x minus A. So we are looking for a vector x star such that the angle must be greater than or equal to half pi. So in this case, x star may like this. Also, it is possible that x star will go down here and the angle both are half pi. So for the first example here, x star have two cases. All right. Of course, any positive scalar of these vectors, they are also normal vectors. Similarly, we can consider the case that if we move this point A to the end of this set, you can similarly find out that the normal vector is actually any vector starting from BD and you turn right until BE. They are all normal vectors. Now, the normal cone consists of normal vectors. So we have the definition of normal cone here. And if this point A is inside of C, then we have the normal cone defined like this. Okay, it actually consists of normal vectors. However, if A is not a point in C, then we define this normal cone as an empty set. This is the definition for the normal cone. Similarly, for the two examples here, we can actually find out the normal cone of line segment AB at point A, and also the normal cone of point AB at B. Okay, so I think we take the second example to take a look. So for the second example, this is the endpoint B and this is A. All right. So all the x will take the direction like this. And for all the regions in this part, they will form the normal vector of B at point B, right? So this is the definition for normal cone. Now, let's take a look at the second type of cone called the polar cone. The polar cone actually is defined as a simple case than normal cone. So in this definition, let's take a look at the condition here. So it's actually looking for the vector y such that the angle between y and x is greater than or equal to half pi, right? Because the inner product is smaller than or equal to 0. So for any x in C, right? So given the set of C, then we should find the polar cone of C. Now, let's take a look at this particular example. We got a cone K here, okay, which is a ray actually. And if we try to find the normal cone, so we just need to take the vector which form the angle of half pi here, okay? So this is half angle here, and this is half angle here. So all the vectors below this line, they actually form the polar cone. Now let's take a look at the dual cone. So for dual cone, it's defined similarly as the polar cone. However, let's take a look at the condition here. The inequality is changed from smaller than equal to greater than or equal to, okay? So in other words, the angle between x and y is smaller than or equal to half pi, right? So kind of swap over. Now we still take a look at an example here. So you got K, a cone in this dark area. So this is a cone. And we try to find out the dual cone. So for dual cone, we are looking for a vector that is from the angle smaller than or equal to half pi, okay? So take the element in K as this vector here, then you got a vector here. And also, if we take the vector in K here, and we take the angle as half pi, then we got a vector there. And the two vectors between all the two vectors, they will form the dual cone, right? Similarly, we can swap the dual cone by adding a sign, then we will get the polar cone, right? So the polar cone and dual cone, they're kind of swap. Now, this is a typical cone. We call it an ice cream cone or a second order cone. And if the dual cone is the same as this itself, then we call it self-dual cone. The ice cream cone or the second order cone, it is actually a typical example of self-dual cone. Now, let's take a remark about the relationship of dual cone and polar cone. So this is the definition for dual cone and polar cone. So we summarize them here, and let's take a look at the sign here. So for dual cone, it requires the inner product to be greater than or equal to 0. And the polar cone is to take the other direction, right? So if we add a minus to the dual cone, we actually reach the polar cone, and vice versa. So in other words, we can verify that the polar cone and the dual cone, they have the following relationship, that if you add a minus or add a sign between one cone, then you reach another, all right? So it is a very interesting case. Now, this is the end of the third part of chapter 1, and in this part, we mainly introduce the cone and the 3 different cones, including the normal cone, the polar cone, and the dual cone. So finally, let's make a brief summary about chapter 1. So in this chapter, we are actually at the beginning of this course. We mainly introduce what is optimization and different ways to do the classification of optimization problem. And finally, we also give some preliminaries in convex analysis, basically different kinds of cones, which we will use later in other chapters. Okay, so we stop here for this lecture and see you next time.